All right, it's great to be here this week. It's really been a fun time, really memorable. I've known Sarah and Dave also for a long time. I met them each when I was a graduate student in the early 2000s, and they were postdocs. And we had lots of really fun and interesting science conversations in those years, and when I was a postdoc, and they were young faculty members, and it's really been fun for me to engage with them over many years, and they're super deserving of this amazing prize. So it's great to be here to share that with them. And there we go. So I'm coming to you from University of California, Santa Cruz, where I'm the director of the Other Worlds Laboratory. That's a summer research program we do every year. And I'll be talking to you about work that we've been doing in terms of modeling the atmospheres and interiors of a wide range of planets. So sometimes people show a slide like this, thinking about why we're trying to characterize planets. Sometimes you can break this down into sort of big picture themes. One is really, how do planets work? What is the physics and chemistry that causes planets to evolve and change over time? And also, how do planets form? And these two things are related to each other. You certainly can have interesting initial conditions that can alter how a planet evolves and changes over time. And today, I'll be talking about things that sort of touch on both of these topics. So I was sort of thinking about what to talk about today, and in the end, I decided to talk about the ways where the solar system and exoplanets complement each other to try to answer some of these big picture questions about the interiors and atmospheres of giant planets. So I'll spend maybe 20 minutes talking about various aspects of giant planets, and maybe the last 10 minutes or so talking about rocky planets. So for giant planets, one of the things we'd like to know is, what's their structure and composition? How do they form? So I'll be talking today about the gas and the solids that they accrete. So because I'm talking to a bunch of astronomers, I'm going to talk about metals. Those are the things that are heavier than helium that are going into forming planets. What are these metals, and where are they within the planets themselves? And then I'll be talking about why do rocky planets have atmospheres, or maybe they don't for some planets, and how do they originate and evolve over time? So first, we'll start with this part here. This is a textbook representation. I think it's actually really from a textbook of what the interior of Jupiter and Saturn were thought to be like. Jupiter's over 300 Earth masses. Saturn's about 95 Earth masses. They're mostly made up of hydrogen and helium, and the high pressure phase of hydrogen is liquid metallic hydrogen, a sea of protons and electrons. That's where we think the dynamo is generated for both of these planets. But we have very good evidence that both planets have a core that's maybe something on the order of 10 or 15 Earth masses, and that core is, we think, made of rock and ice. And we think that core was very important in the formation of these planets. And so Jupiter and Saturn are, of course, are close to home examples of gas giant planets that we're studying in many other solar systems. This is what our textbook view of what we think they might look like. There's a very famous paper from 1996 that describes in detail how we think planets like this form. This is actually the most cited paper in the history of the journal Icarus. It's a really nice paper, and it also was very fortuitously timed to come out right when exoplanets were being discovered. So this paper is entirely about forming solar system giant planets, and at the very end, there's a very interesting paragraph that exoplanets have been found. This is probably relevant to those planets as well. But the basic idea of this paper, and other papers had come before this, which was worked out in a fair amount of detail, is if we look at time in millions of years, so 0, 2 million years, 4 million years, this is Earth masses. This is forming like a Saturn mass planet. We have three lines. We have the solid curve, the dotted curve, and the dashed dot curve. So within the framework of this one-dimensional model, what's forming first is this core of about 20 Earth masses or so. And this core of about 20 Earth masses then starts to accumulate hydrogen and helium. That's the dotted line. And as you accrete more and more and more hydrogen and helium, and the dashed dot curve is the total mass, and this shoots up to about Saturn's mass or so. Within the framework of this model, you're accreting about 20 Earth masses of metals right away. Then while you're accreting the hydrogen and helium, you're also accreting something like 10 Earth masses of additional metals. So in the framework of this sort of model, giant planets should not be the same composition as their parent star. They really should be enhanced in metals because they're forming the midplane of the disk, and they're accreting solids as they're accreting the gas. This is sort of our standard framework for thinking about these sorts of giant planets. And Willie Benz here in the front row, his group over the past 20 years has done a lot of really important seminal work in extending a lot of this framework to exoplanets as well. If you think about our own solar system, again, thinking about the composition of the atmospheres that we see, this is a plot showing a bunch of different elements. We have the noble gases, we have some other volatile gases. This is ratioed to what we see in the sun. So if the atmospheres of our solar system planets had the exact same composition as the sun, they would sit on this direct solar capture 1.0 line. From the Galileo entry probe that dove into Jupiter's atmosphere in 1995, we actually know that Jupiter's atmosphere is enhanced by about a factor of 3 in all of these metals compared to the sun. Saturn, we have never had an entry probe, but from spectroscopy, we see it's around 7 to 10 times solar. Uranus and Neptune, I'm not really going to talk about today. They're so cold, we can barely measure anything in their atmosphere because most everything else is condensed out into clouds. Their visible atmospheres are about 50 Kelvin. The thing we can measure is methane, and that tells us the carbon abundance, and that's around 80 to 100 times solar. So in our solar system, with a sample size of 4, which is always dangerous, as we go to higher and higher mass giant planets, that metallicity enrichment becomes smaller and smaller. The lower mass giant planets are the most metal enriched, Uranus and Neptune. And the reason why this diagram is important is that it really took us from trying to do qualitative models of giant planet formation to quantitative models of giant planet formation and trying to understand why you would have these important relative ratios of these sorts of elements. We can look at a pie slice diagram of what we think Jupiter and Saturn look like from a textbook. This is from a review chapter I wrote a while ago. And so we look at Jupiter's atmosphere. It's about 3 times solar in the visible atmosphere. Saturn's about 7 to 10 times solar. There's some helium that's moved around over time. We're not going to talk about that today. But in this sort of schematic from about 2016, we thought Jupiter probably had a core, but it was very uncertain as to the mass of that core, and Saturn as well. And so what we've learned from the Juno and Cassini missions over the past 10 years or so is that this picture is not nearly sophisticated enough. And so what we now know is that both planets have what people call a dilute or squishy or diffuse core. That both planets have a gradient in this amount of metals or heavy elements that extends about halfway up throughout the planet. The size of this core of heavier elements is around 10 to 25 Earth masses in Jupiter and around 12 to 20 Earth masses in Saturn. So this is our new sort of textbook view of what's happening on the inside of Jupiter and Saturn. I want to talk a little bit about why we know this for Saturn, because I think it's sort of a fun example of looking at solar system planets with a fresh point of view. So the Juno mission is at Jupiter right now. It got there in 2016. It's in a 50-day, highly eccentric orbit around Jupiter. It skims really close to Jupiter's cloud tops. And getting in really close is important because you can see the deformation of the planet's shape due to its fast rotation. And that tells you something about the interior density profile inside the planet. The Cassini mission to Saturn ended in 2017, but we have a wealth of data from that mission that's still being pored over. And also, Cassini eventually got into a very close-in orbit around Saturn, again, very close to Saturn's cloud tops. And so I want to talk over the course of a few slides about a project led by Chris Mankiewicz. Chris got his PhD at UC Santa Cruz with me, working with myself and Mark Marley. And so the typical way one tries to understand the interior structure of a solar system giant planet is from the gravity field. You're looking at the perturbation of the planet's exterior gravity field because the planet rotates fast and it becomes oblate, like we heard about before. And that oblateness tells us something about the density profile inside the planet. It turns out there's a whole nother way to think about trying to infer the density structure inside of a giant planet. And that only can happen if it has rings. Thankfully, Saturn has this amazing ring system. And so the idea is that Saturn's rings, most of the features in Saturn's rings are due to resonances with moons orbiting well outside of Saturn's rings. But it turns out there are features in Saturn's rings that can only be due to perturbations interior to the rings, not exterior. And that brings us to the field of Saturn ring seismology. The idea is that the giant planet is always shaking with a range of characteristic frequencies. We don't really know why this is. In the sun, we can do helioseismology. In the Earth, we do seismology, which is powered by earthquakes. In the sun, we have helioseismology, which is powered, we think, by the stochastic noise from convection. In Saturn, it's not really clear what's driving the oscillations in the planet itself, but there are things called F modes, which is similar to a water wave. And what this is, these are waves, they are internal oscillations of the planet. As the planet rotates, it drives gravity perturbations in the rings. And this was originally all worked out in Mark Marley's PhD thesis in 1990, and eventually come back to by Chris Mankiewicz and Jim Fuller in the past several years. And so Saturn's non-radial oscillations tell us about the interior density profile. And I can't go into all the details today, but this allows us a very exquisite probe of the interior density profile by looking at dozens of features in Saturn's rings that tell us about the interior density profile. And you can use this to make a picture of Saturn's interior today. So the top panel is Z, the metal's mass fraction, as a function of radius. And so we can see a hydrogen helium-dominated outer layer with a very low metals mass fraction, and we think there's a gradient all the way into the center of the planet. This is the density profile, density versus radius inside the planet. This is a measure of the Brute-Vassallo frequency, which I'm not going to talk about today. But the constraints of the density profile with and without seismology are dramatically different. I can show you without seismology from a paper with a postdoc of mine from 2020, and then with seismology, the density profile is tremendously better constrained in the interior. So we have extremely strong evidence for a dilute core and composition gradient in the interior of Saturn. We think the same thing is true for Jupiter. I would say the evidence is compelling, but not quite as strong due to the lack of seismology. But this is our new paradigm for what we think giant planets are like in their interior. This has led to new hydrodynamic work. Here we're doing at Santa Cruz with a collaborator, Pascal Garrod, a postdoc, Menadini, and a grad student, where we're looking at the stability of these sorts of composition gradients over time. This is the gradient in the abundance is this is height versus density, And over time, what we find is that if any part of this gradient becomes convective, quickly the whole thing becomes convective. So what we believe is that what we're seeing today after 4.5 billion years is a remnant structure from formation. It's not a compact core that's been dredged up over time, because that dredging would actually lead to convective overturn. It would really ruin the gradient. So we think we're seeing a vestige of the planet's formation, although this is very much work in progress. So if you wanted to make a cartoon of what we think giant planets are like from our solar system examples, is that there might be some sort of, this is the mass fraction at the center, and then this is the surface. This is, again, the metals mass fraction. So perhaps there's a pure core of some undeterminate size. There's some dilute core with metals and hydrogen mixed together. And then there's the envelope, which also has metals and hydrogen mixed together. I mentioned the visible atmosphere in Jupiter and Saturn are enriched in metals compared to the sun. So in Jupiter and Saturn, this is around 15 to 20 Earth masses, and then we, of course, have the visible atmosphere. So the giant planet connection is really thinking about how we can measure these atmospheric abundances for exoplanets, and how we can constrain the bulk metallicity of the planet, again, for exoplanets, with a much larger and more diverse sample size, but without, of course, as much detail. So the visible atmosphere, for exoplanet atmospheres, we can characterize those atmospheres to measure the abundances of a range of different elements. We can also use exoplanet structure models to tell us something about the total metallicity interior to giant planets as well. And this is a plot of the mass-radius diagram. This is mass in Jupiter masses versus radius in Jupiter radii. This is a current as of just a few months ago by Daniel Thorngren, who's a postdoc at Johns Hopkins. He originally did his PhD in Santa Cruz a few years ago. And this is actually color-coded by temperature. This is the incident flux. Planets under very high flux are red. Planets under very low flux are in blue. And there's, of course, a very striking aspect of this diagram that the hottest of the hot Jupiters, the hottest ones, are the most inflated, and the ones that are relatively cooler are not inflated. That's a something I'm not going to talk about in much detail today, but it's been an interesting problem over the past 20 years or so. It turns out there's a subset of these objects, mostly the ones that are relatively bluer, where we can use structure models to infer the bulk metallicity of the planet. We can measure the mass, the radius, the density. We can assess the age from the parent star's age. You can build a structure model that matches these things, and that allows us to infer the bulk metallicity within these planets. And this is something that we did with a much smaller sample size, apparently quite a long time ago now. Time flies. Where we're able to, a particular planet like WASP-8, we can assess the total amount of metals within the interior of the planet. This is a relatively massive planet. This is a relatively lower mass planet. We can do that for a wide range of objects to assess the amount of metals interior to the planet. And you can make a diagram like this. This is planet mass in Jupiter masses. This is a Jupiter mass. This is about a Saturn mass. This is a tenth of a Jupiter mass. This is the amount of heavy elements or metals we infer inside the planet. And we can actually compare that to what we know for Jupiter and Saturn. This is Saturn right here, and this is Jupiter. So what we see is that Jupiter and Saturn fit in relatively well amongst their cousin planets. But also we can see is that as giant planets become more and more massive, they still keep accreting more and more metals. So you shouldn't just think of a giant planet as being a core with a bunch of hydrogen on top of it. When you're accreting the core and you're accreting the gas, you're also probably accreting a lot of additional metals that enriches the whole envelope. And so we can have apparently giant planets with dozens or perhaps even 100 Earth masses of metals inside these relatively massive giant planets. And so then you can make another diagram of what you might call the metal enrichment. This is the metallicity of the planet compared to the star, Z planet over Z star. If all the planets had the same metallicity of their star, they would sit along this line here, one-to-one line at the bottom. But indeed, they're metal enriched compared to their parent stars. This is Jupiter and Saturn right there. So again, we see relatively nice agreement between the cousin planets and Jupiter and Saturn themselves. So heavy element or metal enrichment is the hallmark of all giant planets. What's interesting to me is the tremendous amount of spread we have here. There's really no one way to make a Saturn or one way to make a Jupiter. You can have relatively metal poorer versions. You can have relatively metal rich versions. And one of the things that's exciting to me as we get to ever larger sample sizes is thinking about cutting this diagram into maybe the eccentric planets versus the circular planets. The ones around lower mass parent stars, the ones around higher mass parent stars. We weren't able to do that with our smaller sample size 8 years ago, but the sample size is growing and probably have about 5 to 10 times more planets now that we could do this for than we did in 2016. And my slides are slightly out of order, that's fine though. So we want to complement what we're doing in the interior with what we can do in the atmosphere. And that's the era we're in now with the James Webb Space Telescope. I mentioned before, we can look at that slide for Jupiter's abundances for a bunch of different elements in the visible atmosphere. We can start to make similar diagrams for other planets as well. This is a paper led by Luis Wellbanks, who's a postdoc at Arizona State University, part of the Manatee collaboration, a very tortured acronym I don't remember off the top of my head. It's mid-infrared, it's got a lot of stuff in there, right? So transits. So this is for WASP-107b. WASP-107b is about twice the mass of Neptune. It's about 40% of the mass of Saturn, a relatively low mass giant planet. And this is a transit transmission spectrum when the planet passes directly in front of its parent star. And what we're able to do is from about 2.5 to 5 microns, look for molecules in the planet's atmosphere. And indeed, we can see a host of such molecules. There's a feature due to SO2 at 4 microns. This is a photochemical product of sulfur that tells us the bulk sulfur abundance. We can see CO2 and CO and methane. That allows us to measure the bulk carbon abundance. We can measure water vapor and these other products with oxygen to determine the oxygen abundance in the planet's atmosphere. And we can also see a faint signature due to methane that tells us something about the nitrogen abundance in the planet's atmosphere. This is just one particular planet But like I said, for Jupiter, we had the qualitative modeling versus quantitative as we can now measure the abundances of a wide range of atoms and molecules in dozens or eventually hundreds of planets. We can start to compare those to Jupiter and Saturn as well. On the lower left here are just particular abundances as a function of pressures. This is a mixing ratio of CO, CO2, SO2, just a little bit of the details. So we can start to think about the particular abundances of particular elements and thinking about the overall metal enrichment. So you can start to think about a comparison of a plot on the left and the right. So the plot on the left is the plot I showed you before, this metal enrichment as a function of planet mass. This is for the bulk structure from a model comparing to the mass and radius. On the right is a plot I got from Gongwei Fu yesterday, who's a postdoc at Johns Hopkins University. He's been synthesizing all the James Webb data we have up until now, and what he's finding is something somewhat very interesting, very similar to what we see in the solar system, in terms of atmospheric abundances. This is mass versus atmospheric metallicity enrichment. We can see Uranus, Neptune, Saturn, Jupiter. It's the early days, but with about 8 or 9 or 10 points on here, we can see the exoplanet context is so far aligning relatively well with what we see in the solar system, but with a different slope than we found in this Thorngren relation over here. So by combining these two diagrams over time, we can start to assess generically or generally are most giant planet metals in a core, or are most giant planet metals in an envelope? This is things that we can start to do with a much larger sample size as time goes on, as we try to understand giant planets as truly a class of astrophysical object, not just looking at Jupiter and Saturn, but the class of all giant planets. Right on time, 2/3 of the way through. So I think the thing about giant planets is that we really are at the cusp of understanding them as a class of objects. We can put Jupiter and Saturn in context to assess the overall composition of giant planets for planets outside and inside the solar system. We can start to think about more complicated questions, though, about the composition and the evolution of rocky planets. This is a much harder problem to solve that I think will take a much longer period of time. This is a plot that I think Dave showed a version of earlier in the week. This is a plot of what people call the Cosmic Shoreline. This is a plot by Zonley and Catling 2017. It's an empirical plot where you take all the planets in the solar system and you take all the exoplanets, you make a plot of their escape velocity in kilometers per second, and you make a plot of something related to how hot they are. This might be the total amount of UV and X-ray flux over time, or this plot could be something like planetary temperature. It's something about how warm or how much irradiation the planets get. And what's interesting is that you can sort of compare objects that have an atmosphere and things that don't. So Jupiter, Saturn, Uranus, and Neptune, very thick atmospheres, very far from the line. Earth and Venus and Mars, relatively close to the line, especially Mars. Titan, pretty close to the line. Pluto, Triton, really thin atmospheres. Up and to the left, you see things that definitively don't have atmospheres. And there's a wide range of exoplanets sort of on both sides of this line. So this line is empirical from the solar system. We would love to know if the exoplanets here, the terrestrial ones, do they have atmospheres or not? And what are the factors that control which planets have atmospheres today? An important question along those lines is, where do atmospheres come in the first place? And so we think that rocky planets have atmospheres that are outgassed from their interior. We call that a secondary atmosphere. Whereas if you take your atmosphere from the nebula, like a giant planet, that would be a primary atmosphere. And so it's one way to thinking about what are secondary atmospheres made of. Miriam Tellis and I started a collaboration about 6 years ago now. She's a professor at UC Santa Cruz. She recently won an NSF Career Award a couple years ago. And so the collaboration was really thinking about, well, what if we could heat up meteorites? Meteorites where we know precisely what they're made of today. They're sort of relatively pristine pieces of the solar nebula. If we heat them up over time, what sort of gases do they liberate? And so it's not an exact comparison to what a planet would do. Planets form extremely hot. They're probably made of a mixture of different kinds of meteorites. But this is a sort of a simple first step to trying to investigate this problem. So Miriam and I hatched this idea, and Maggie Thompson was an extremely smart and energetic and fabulous graduate student working with us. This has not been announced yet, but I just learned recently she's going to win the Trumpeter Prize from the American Astronomical Society of the Pacific for a recent PhD thesis considered unusually important to astronomy. And that's a really big deal for her and for Miriam and I. And she is a postdoc here at ETH Zurich on the continent. So feel free to invite her up to give a talk. And so what she did was a variety of experiments in heating up meteorites to think about what sort of gases they're liberating. And then part of her PhD was also thinking about that in the context of modeling the atmospheres of terrestrial planets as well. And so again, I can't really get into the details, but these are things where our collaborator, Laura Schaefer, a professor at Stanford, had modeled these sorts of processes. As you take meteorites of different classes and heat them up, what sorts of gases would you expect to be liberated? And these are things we can actually measure in the laboratory. So Maggie and Miriam Tellis have been doing this over the past several years. Of course, Miriam has her own laboratory on campus, and Maggie's been building her own at ETH as well. So this is just very much work in progress as we're trying to build up a more comprehensive understanding. This informs work that we've been doing in Santa Cruz with Josh Christensen-Totten, who was a postdoc with me. He's now a young professor at the University of Washington. And so what Josh has been trying to do over the past several years is build a sort of end-to-end interior atmosphere evolution model. And you can tell from all the wide array of arrows on this diagram that there is a lot going on. And so he's applied this model both to Earth and Venus, thinking about the Earth-Venus dichotomy, and also the TRAPPIST system, which has these 7 transiting planets that all formed in the same disk, some inside the habitable zone, some outside the habitable zone. And this model, of course, any of these parameters are highly uncertain. So I just want to give folks a flavor of why this is such a complicated problem, even in the absence of thinking about life. We have parameters that control the initial volatile inventories. Do the planets form relatively dry or form relatively wet? There are stellar and planetary parameters controlling atmospheric escape, the amount of UV flux from the parent star, how that falls off over time, the temperature at the top of the stratosphere. There's factors controlling the carbon cycle on the planet, which affects carbon-bearing molecules. There's temperature-dependent mantle viscosity. There's parameters controlling the oxygen loss into the mantle. And then the time-evolving planetary albedo, which affects things like the surface temperature. So what we've been doing is, of course, realizing that there's lots of uncertainties. We've been doing sort of Monte Carlo simulations of the wide range of atmospheres you would get for TRAPPIST planets B, C, D, E, F, and G, with the idea that observations over time for this wide range of planets in the system might inform some of the choices we're trying to make. I think one of the most interesting things to me is that we really can find a very wide range of atmospheres that are, of course, controlled by a lot of these parameters. But one of the very most important is actually the initial volatile inventories. One of the things that came up earlier in the week are, do the planets themselves, are they forming relatively dry or are they forming relatively wet? And how do other planets in the planetary system, which might scatter planetesimals into those orbits, how might that affect the initial volatile inventory? And so we're at the point now, this has come up a few times, even today, where JWST can really tell us something about this cosmic shoreline. This is a plot I got from Brandon Park Coy, who is a grad student at University of Chicago. This is all the cycle 1, 2, and 3 observations, both phase curves and eclipse. This is, again, that escape velocity. And there's 2 versions of the diagram. One is just based on how much energy you're getting from the star today, the total amount of energy. This other one is looking at the cumulative X-ray and UV flux compared to the Earth over time. And for the objects that we're looking at in cycles 1, 2, and 3, the idea is, because a lot of those are around M stars, and M stars are extremely bright in X-UV flux at a young age, and they get weaker over time. If that is perhaps the controlling force, then all these objects probably sit on the dry side, the no atmosphere side of the cosmic shoreline. If instead it's mostly driven by the temperature today, then you might expect a wide range of planets, some on one side of the shoreline, some on the other. So what's exciting to me is that this is something we can use data today and the next several years of analyzing this data to think about this question of the cosmic shoreline, of which objects have atmospheres and which ones don't, in this decade with the James Webb Space Telescope. So in my last slide, then, I just want to remind everyone that we live in this amazing era where we have space missions going to a variety of planets in our solar system. We have Juno at Jupiter. We had Cassini. We've had missions at Mars telling us about atmospheric escape, the MAVEN mission telling us about how Mars lost its atmosphere. And they're driving our ability to understand things like giant planet composition, with the exoplanet contest allowing us to understand them as a class of astrophysical objects. Rocky planet atmosphere, origin, and evolution is really a multifaceted problem. Even in the absence of thinking about how life might alter those compositions, we have a lot to learn of thinking about these processes in terrestrial planets generally. But with laboratory work and the James Webb Space Telescope and new models, and I think we're also going to need a lot of patience, but I think we will get there. So thanks so much.
So I've been following this Jupiter has no core thing, or it has a dilute core more than half its radius, which obviously is not the definition of a core, but we still call it that.
Yeah.
So what I'm wondering is, how does it form? If you're going to claim that it's not formed and then later destroyed, how is it forming with so much hydrogen mixed in with everything, instead of that picture of the rocky formation? And I have a follow-up question.
Yeah, that's a great question. So people are still trying to come to grips with that in terms of formation. There's a very nice paper by Ravit Haled and Dave Stevenson looking at the concurrent accretion of solids and gas, where they make the assumption that as you're accreting those materials, they're sort of staying in the relative mass fraction you accrete them in. And if you sort of just do that without really worrying about is it hot enough for them to mix, then you would get a natural gradient like that. But it might in the end tell us something about the initial temperature of those planets if they don't end up mixing.
Interesting. Well, theorists can come up with anything, of course, so yeah.
Yeah.
Well, my second question is, we have brown dwarfs, we're going to hear about those later, and we have a lot of details. But do we, is there anything, because you're doing exoplanets and solar system planets, but we can do exoplanets and brown dwarfs and see in comparison how much metals or even things like magnesium, calcium are in the envelope. Will that tell you something about how planets form versus brown dwarfs?
I think so, yeah. So, I mean, Jackie, of course, will talk about this, but, probably planets have a range of metallicities to maybe a little bit metal poor to much higher metallicities. The brown dwarfs are going to be typically solar metallicity, but I know Jackie's been working on some that are very low metallicity. And so I think thinking about that continuum of metallicity and looking at the chemical... Yes. So, a brown dwarf, we think, is probably a fully convective object that doesn't have any core at all. And so evolutionary models, in principle, should work in a relatively straightforward way, whereas a giant planet structure and evolution model probably has to deal with the fact that there's this core. So you would probably have divergent evolutionary histories for two things that were the same mass but formed differently.
Thanks for the talk. It was really interesting. I'm an Earth scientist, so I know very little about Jupiter. But I was wondering, what does it mean for the dynamos that these planets generate, that they have this dilute core or a squishy core?
That's a fantastic question, and that's really thrown the whole field for a massive loop in the past several years. So the old idea was that, you had a relatively small core, and then you had this huge, for Jupiter, 250 Earth masses of liquid metallic hydrogen, and you had just this sort of massive dynamo. What people are furiously working on now in both planets are models where, let's say, the inner half is statically stable and it cannot participate in the dynamo. And then you have a shell that is maybe just the dynamo. It gets even more complicated because we think there might be a helium gradient. I would say people are working on it, but it has been a really exciting time for and a lot of change. But people are able to create, as Sarah said, modelers can do a lot of interesting stuff. So you can make models that still look like what we see with a range of different geometries, I would say.
Okay, so at the end, so I'm very interested in this idea of the cumulative X-ray emission
Yeah.
that exoplanets experience.
Sure.
And I think I want to caution that there are parameterized laws about how stars spin down and how their X-ray emission decreases over time. And because I think in part those are convenient to use,
Sure.
that they get abused because they are incorrect. And instead, what we're really finding with stars, at least all the M dwarfs, is that they do not change their X-ray emission over time. They are absolutely constant. They are saturated. And then they stop.
Sure.
And so in that plot, I just wanted to check, are you, just encourage everyone
Yeah.
to really be up to date with what the observers are learning about, what the history of angular momentum loss is for a TRAPPIST-like star, and not just use one of these parameterizations, which really go back to Schematic and what the sun is doing, which is a totally different physical object. So how, I'm just curious, in making that plot, how are you parameterizing it? How are you approaching this? That would.
I borrowed it from Brandon, so I do not know the answer to that question, but I will follow up with him.
Thanks.
Yep.
Well, let's thank Jonathan
thanks.
again.